Hi, welcome to the Physionic podcast. My name is Nicholas Verhoeven. I'm a PhD student in molecular medicine. I have my master's in exercise physiology, and I do cell biology, molecular biology research at the University of Maryland School of Medicine. And today, we'll be discussing a few different topics. The first topic that I'll be discussing is I'm going to label it mapping microbes because that's how I'm going to name it when I'm creating the Instagram or releasing the Instagram content on it. Which, by the way, if you're not following me on Instagram, you're missing out on daily content. Every day I post some new information, which is hopefully informative, interesting, useful, any combination of those three or all three. And that is, of course, linked to this content, so you can just click on the link and go and follow me. With that said, the next topic that I wanted to discuss is muscle size and why muscle size, although it correlates extremely well with strength, why it isn't the only factor that leads to strength. And I'm debating if I'm going to talk a little bit about the athlete's paradox, which is a piece of content that I released a few days ago, talking about the athlete's paradox, the similarity between obese individuals and athletes. I might touch on that. But anyway, if I decide to, you can always skip to each section because I'll have the timestamps for you so you can skip to the section that you'd be most interested in discussing. Mapping microbes. So what researchers did is they took two different strains of mice, and in one strain of mice, they essentially got rid of all the bacteria that are inside of our body, because you've heard of the microbiome, I'm sure. Microbiome is something that a lot of research is being done on now. And this was really cool because they essentially got rid of the microbiome in one mouse, and then they left the microbiome completely intact in the other mouse. And then they wanted to know, well, how much of the molecules that are used to communicate between cells. So to give you a bit more context, your liver cells can communicate to your muscle cells can communicate to your neurons. I mean, every cell in your body is constantly communicating with one another, and that's what we consider endocrinology. That's what we consider hormones. That can be in a paracrine fashion, an endocrine fashion. Most people think of an endocrine fashion because it's traveling through the bloodstream and going to another area of the body. However, there are situations like paracrine wherein it's moving a shorter distance, so it's really pretty local. An autocrine fashion where a tissue will release molecules, communication proteins, communication molecules, and will bind to themselves, so they're kind of communicating within that local environment. And now there's actually intracrine actions, which is a bit confusing because cell signaling, I guess maybe it's cell signaling within a particular cell. It's just kind of communicating with itself, which I don't really understand why we need a specific term for that, but maybe there's some distinction that I'm not familiar with yet. But regardless, you know that cells communicate back and forth with one another, and they send these what are called communication proteins known as cytokines. I've said that many, many times before. So cytokines, chemokines, there's another term, but I can't think of it. Anyway, the word kine for communication between different organ systems, different cell types and things of that nature, to essentially kind of, it's almost like updating the body on like, oh, what's going on in this region of the body, what's going on in this region of the body, et cetera, et cetera. And we can do that through like electrical signals through the neurons, but we can also do that and through neurotransmitters, but we can also do that through what I mentioned, the endocrine fashion, the endocrinology, where we send signals from the cells independent of the neurons, independent of that electrical signal to the rest of the body. So these researchers wanted to find out, well, how many of these molecules, how much of this molecular crosstalk between different tissues, different organ systems is due to our cells as opposed to like bacteria that are part of our body essentially. And fascinatingly, by this comparison of the microbiome less mice compared to the microbiome-rich mice, you have they were able to distinguish which ones were the same, which would imply that those were not part of the microbiome. And then they were able to determine which ones were part of the microbiome by doing, I believe they probably did a technique called mass spectrometry. That's a mouthful. Wherein they're able to distinguish many, many different molecules just by the mass, the literal weight or the composition of the molecule. So you can have thousands of molecules and get the masses for each one and get an idea of what that molecule is. So, and then you can cross compare between the two mice. And then once you have like an array of different things that you want to look at, you can then try and attribute that to particular gene sequences. So then they're able to attribute the microbiome-less molecules to the cells that release them because they have the genetic material to release them, to create those proteins and then release them into the bloodstream. Now, fascinatingly, what they found is that anywhere between 20, and there's a pretty big range here, but even with 20 to 70% of the molecules across these organs were foreign, quote unquote, foreign to the mouse. So they weren't actually produced by the cells of the mouse, they were produced by something other, and presumably in this situation, that other is the bacteria. So what a crazy thought to think that your bacteria are, at the very least, releasing a pretty sizable percentage, and maybe even more than half of the communication proteins that are going on in your body. So this opens the door. This we've already known the microbiome was important, but this really opens the door that the microbiome may be unbelievably important. I mean, just have like we may be. This is like equivalent to discovering, I don't know, like some other galaxy, and you know that gives us some idea of our own galaxy and our own existence. You know, for the human body, or discovering something in the depths of the ocean that we never knew before. We find out aliens are, you know, in the depths of our ocean, like something like that. It'd be so extreme of a realization that our microbiome may have such profound impact on our health that we've thought of the body in the past as this kind of stationary thing that's just our cells communicating back and forth. But no, there's also crosstalk with all the bacteria in our body, and the fungi and all kinds of other things. So I feel like I say fungi and then I say fungi sometimes. Whatever, you get my point. So, I mean, what a remarkable thing to think about, that our body is so much integrated with this thing that's outside of our body. I mean, technically it's inside our body, but it's not part of that. It's not part of the eukaryotic system, if you want to go down to simple biology, that makes up us. It's just billions of prokaryotes. It's billions of different unicellular, I don't want to call them organisms, but I guess I will, organisms that live inside our body and may have a profound impact on the entire eukaryotic system that we are. Like, that is such a cool thought to think. So we have so many more discoveries within our own body. Like, we're looking at space, we're looking at oceans, we're looking at oil, we're looking at, you know, archaeology, we're looking at all these different things, and we think we got like health figured out. And like, I think on a surface level we're getting there. Like, we're understanding, you know, certain things are bad. Like, if you overconsume continuously for your entire life, that is bad. Like, I mean, we get that much. But in terms of the real intricacies, we've studied so much more of how our cells communicate, and we have, like, the landscape for that is still wide open. And now we've added this other layer on top of things. So microbiologists and microbiome researchers will really be able to start trying to figure out some of this crosstalk between these bacteria and our cells. Really, really freaking cool, gotta admit. Okay, so that was the first topic in all reality, or topic 1B. The next topic is to discuss muscle size and its relationship to muscle strength. I've gotten this question in the past before, but I just recently released a piece of content and looked at the association. So again, not causation, but the association was quite strong, really strong actually, between muscle fiber or muscle cell size and increases in squat strength. And so it was like 0.8 or 0.85 correlation, something like that. It was like really, really strong correlation between the two. And that's not too surprising. Even I think somebody even commented like, well, why did we even do this study? Well, I discussed that last podcast episode for the many reasons, or several of the reasons why we did this study. We as in the scientific community. But I wanted to address kind of muscle size, like why doesn't muscle size immediately be a perfect correlation? Why doesn't it exactly cause increases in strength? And actually, technically, it does. It does lead to increases in strength. Like having a larger muscle tends to mean that you have greater strength. And that bears out in the literature, not just in that piece of content, but bears out in other pieces as well. However, it doesn't account for all of the increases in strength. And a prime example of this anecdotally that a lot of people have likely seen is somebody who's relatively skinny or seems relatively small, yet they're, let's say, squatting 405 or something like that. And it's just like they have this explosive amount of strength. And the reason for that are multifaceted, but one of the main reasons is because of the recruitment of the muscle fibers can be substantially different. So you have a neuron that comes down and innervates or interacts with a muscle cell, or actually it interacts with, let's say, a series of muscle cells. So if you can figure out a way, and this is really detailed by just strength training, that's how you figure out this way, by activating more of these muscle cells at a given time, that means that those muscle cells will be under less stress, under less strain per repetition lifted, but will be able to still lift that weight. So instead of relying on, let's say you've got 10 muscle cells, total muscle cells, which would be an insanely low amount, but I'm just trying to simplify things. And you end up wanting to lift a particular weight. Those neurons can activate, let's say, just 3 of those muscle cells and lead to lifting that weight. Or it can alternatively spread that out across, let's say, 8 of the muscle cells. Now, of course, those 3 are going to have to work really hard, but if you spread it out to 8 muscle cells, suddenly you're getting force production from a multitude of different muscles. So there's a huge difference in how muscles are able to lift a weight up, and they don't have to necessarily be this massive muscle belly to be able to do that. Now, again, of course, the bigger the muscle, you will see increases in muscle strength, but in terms of it accounting for everything, it doesn't account for everything. And that's why you have some individuals that are pretty skinny or pretty small, and yet they can outlift a person who's really muscular. Like, for example, in certain lifts, I'm not very strong. I'm not a great squatter by any means. My deadlift is quite strong, but my squat is trash. And another example for me is my barbell bench press is pretty much trash, but my dumbbell bench press is really good. And I think that part of that is, of course, psychological, but a lot of that, I think, comes down to me feeling the motion a lot better, like feeling like I have control over that motion a lot more. And I think in those regards, you've probably heard of like muscle-mind connection. I do think that plays a big role, being able to consciously force your body into a situation where it's using more muscle fibers to lift a particular weight, or using less muscle fibers but contracting them even more. It's not like you sit there and decide, Well, now I will use 5 muscle fibers, but you can still have on a certain gradation level. Like if you try and lift a weight really quickly, the same weight, let's say you're trying to lift 80 pounds and you lift it, you just lift it because you know you can lift it, as opposed to when you lift it really quickly. When you lift it really quickly, there's a power component that comes to that. So suddenly it's distance by time. So with the power component, there's the time addition there. And for that weight, even though it's the same weight, for it to move from point A to point B, from the bottom of the repetition to the top of the repetition as quickly as possible, you're going to have to recruit a lot more muscle fibers to move that weight to that position, because you're trying to move it there as quickly as possible. You're not satisfied with just getting it there. It's not like you're a taxi driver or a bus driver. You don't want to just lift the weight. You want to move it as quickly as possible. So you're like the Ferrari or the Lamborghini or Porsche 911 or 918 Spider. What a beautiful car that is. So hopefully that made some sense, that it's how the muscle cells are innervated and how they're activated that does make a big difference in terms of muscle strength. So hopefully it offers a little bit of an explanation as to why there is variability, where it's not just muscle size immediately means that, you increase your muscle by 15%, therefore your strength will increase by X amount. Like, it doesn't work that way. Okay, finally, I guess I will talk a little bit about the athlete's paradox. I think that this is such an interesting thing that occurs in between athletes and obese individuals. So I released content on this a couple days ago, video content on this. And the athlete's paradox is essentially a situation where an endurance runner or endurance athlete of some sort has a particular adaptation that is the same adaptation, at least on the surface, the same adaptation as an obese individual. So a person with obesity will have the same adaptation as a person who is really, really athletic. So first off, what gives? And second off, what is that adaptation? Well, let me start with the latter. So the adaptation is a filling of the musculature with what are known as lipid droplets. So you have these vesicle, like round structures that are found within the muscle cells, and they're filled with actual macronutrient fat. They're actually filled with saturated fats and polyunsaturated fats. I mean, the things that you literally consume. And I don't want you to make the association that because you're eating these fats, that you're suddenly filling your musculature with fat. There are certain drivers, physiological drivers, independent of your nutrition, that determine this. So again, I'm just trying to make sure that people understand that, because I feel like sometimes people think of things too simplistically. They just say, if I eat fat, then it goes into my musculature, and then I have this bad thing happen. It's not that simple. I'm going to leave it there, but if you've got questions, you're more than welcome to contact me, and I will certainly be covering stuff like this in the future as well. So anyways, you have these lipid droplets that end up finding their way into the musculature, or more like they're formed most likely by the musculature itself. And they're filled with these molecules of fat. So the lipid droplets are sacs, essentially, and inside those sacs are the fat molecules. So people who suffer from obesity have this, and heavily trained endurance athletes also have this. So what gives? Why do we have this similarity? Well, it turns out that with obese individuals or people with obesity, most likely what's happening here, and again, this is most likely what's happening, is that they've been over-consuming for such a long time that eventually their fat cells, which is not to be confused with macronutrient fat, those are not the same thing. Their fat cells, their adipocytes, end up getting so big that and they've split so many different times. They've created more fat cells that they can't contain more fat. And therefore, they end up, in a manner of speaking, in a non-anthropomorphized way, they reject the storage of more fat within them. So suddenly, where is this fat going to go? It's just stuck in the bloodstream. It's high levels of triglycerides, high levels of free fatty acids. So now it's stuck in the bloodstream, and what could add to that, what could exacerbate the issue, is that these adipocytes will release fat, will undergo a hydrolysis reaction. So when they're storing, they're going through esterification, and when they are hydrolyzing these fats, they're releasing this fat into the bloodstream. So it is also possible that adipocytes are so full they're actually releasing some fat because they literally can't hold on to it. So where is all this fat going? Well, I already kind of gave the answer away. It goes into the musculature, so it finds its way into the musculature. So a really cool adaptation for storage, because the body knows it can't keep all these fats in the bloodstream. Just think about how much fat ends up in the bloodstream. That would be absolutely terrible. That would cause all kinds of different issues with all these fat molecules circulating in your bloodstream, especially when you have to get all these different things like, oxygen, CO2 removal. You have other nutrients that need to get through. I mean, you need to get rid of acidity. I mean, there's all kinds of different things that your bloodstream is there for. The movement of immune cells is another one. So a lot of different things, a lot of other cells, hormones. I even talked about this earlier in this podcast episode. So then they end up storing it in the muscle cells specifically, inside. So not outside, but actually inside the muscle cells, in these lipid droplets. Now, an athlete has the exact same thing, but look at them. Like, they're so skinny. They're like rail thin. They have like no fat on them. So what in the world, how are these fats, how are these adipocytes rejecting this fat? And it's ending up into the muscle cells. Well, I don't actually know the mechanism for why that happens yet. I don't understand it yet, but what I can say is that it's a physiological adaptation. So as opposed to a person with obesity, where it is a pathologic adaptation, it is a necessity. The body needs to find an area to put this fat, to store this fat. With the physiological adaptation, the person who runs so much that their muscle cells have essentially decided, if you'll allow me the liberty of muscle cells deciding, the muscle cells have been driven to say, you know what, screw the fat storage in the fat cells. Those are all the way in Kentucky. We want them closer to us. We want them right next door. We want them in the same city as us, so that we can get this exchange of fat for metabolism. So we can actually get this exchange of fat for the use of energy, for the production of energy. And that's essentially what they do. These lipid droplets don't end up in the same place within the muscle cell as the obesity-driven lipid droplets. Those tend to be found in a more useless, quote-unquote, useless section of the muscle, right on the surface of the muscle cell, on the inside, on the sarcolemma, the cell membrane of the muscle cell. However, with these athletic lipid droplets, they tend to be found right next to the contractile units that allow the contraction and the movement of, well, for example, the leg muscles. So it's a really interesting change. Like, while on an overall scale, it seems like the same thing is happening, but on a subcellular level, it's not the same thing, because mitochondria are congregating around these lipid droplets for the athletes. And most likely what's happening is you have this quick exchange of fat. So probably not nearly as quick as like glucose or sugar metabolism for, going through glycolysis, which is independent of the mitochondria for the most part, but does allow the removal of fat from these lipid droplets and to move them into the mitochondria to be metabolized to produce adenosine triphosphate, to produce energy. So a really, really cool adaptation and a big difference between the two. Again, one is pathological in the obesity condition, and one for the athletic condition is a supremely interesting, fascinating mechanism by which mitochondria and the muscle cells are kind of working together to convince these lipids to end up setting up shop right next to them instead of setting up shop somewhere else, where then they have to be shuttled into the bloodstream and then find their way into the muscle cell. So what a cool concept, though. What a cool concept. And if you haven't checked out the visuals and all that I've got for that piece of content, then I strongly, strongly encourage that you check it out. Okay, that's what I've got for you. Hopefully you found this informative. Hopefully you found it informational. Well, that's the same as informative. Informational, interesting. That's the word I was looking for, and maybe a little bit useful as well. With that said, I will hopefully have the pleasure of speaking with you in the next one, and I wish you a wonderful, wonderful day. Have a good one, guys. See ya.